Can you hear me all right? Hi everyone, my name is Yoo Jung Kim and I'm a 5th-year PhD student at UCLA, and I'm very excited to talk to you about a new technique for high angular resolutions. I mean, measuring even below the diffraction limit using a device called a photonic lantern and its on-sky demonstrations at the Subaru telescope. So I'm going to start with this question. How do we recover the spatial information from what we observe? For just normal imaging, where we place a camera on the image plane, what we are doing is we are counting photons in pixel basis, and we are extracting spatial information from there. This is very straightforward, but it's not very optimal at very small angular scales because it discards the phase information of the light. But we can measure the light in a different way, called mode-based imaging or spatial mode demultiplexing, as Sebastian gave a very nice lecture today. In this framework, basically, we split the light according to its spatial pattern of fluctuations or spatial modes, and then we count photons in this mode basis. And it has been shown that it's theoretically much more efficient for spatial information recovery within the diffraction limit than the standard intensity imaging. So in order to do this mode-based imaging, we need a physical device that splits the light according to the modes, and a photonic lantern is a device for that. A photonic lantern is basically an optical fiber, just like this, but it's special in that it has one input and multiple outputs. So we place the photonic lantern at the telescope's focal plane, and then so the light is injected in there, and it splits the light according to the modes, according to its spatial modes. And what it's exactly doing is it's converting the multimodal light into multiple single-moded beams, and the complex amplitudes of these beams correspond to the mode amplitudes. So we have single-mode fiber outputs, so it's easy to just feed these outputs to a spectrometer to get these spectral traces like this. So in this configuration, with the lantern and spectrometer system, we can get the spectral information and spatial information at the same time. So it's like an integral field unit, but at very small angular scales. So we have these devices at the Subaru telescope. In the infrared side, we have one of Young's baby, the photonic IR photonic lanterns feeding a low resolution spectrometer. And in the visible side, we have a 19-port photonic lantern feeding a mid-resolution spectrometer, or it's named First PL. And I'm going to talk to you mostly about this visible device. So I said that we can use photonic lantern like an integral field unit, but in order to say so, we need to be able to reconstruct the image as a function of wavelength. And what we are observing is just these spectral traces. We need to figure out how to go from these observables to actual reconstructed images. This is one of the challenges. And also, this mode-based imaging is very sensitive to any aberrations or misalignments. So we need a technique that's robust to wavefront errors. So these are the two main challenges. But conclusions first, we made this work on sky on actual observations. And we were able to reconstruct this nice high-resolution image of a disk on the star. And we even discovered for the first time that the disk is asymmetric. So I'm going to talk to you about today how we did this on-sky demonstration, and the future directions of what I'm working on after this on-sky demonstration. So we observed a target called beta CMI. Beta CMI is a classical BE star. It's a very hot star, and it has surrounding disk that's very hot and compact. It's very faint in the visible, the disk itself, but it has strong H-alpha emission line. It's double-picked because the disk is rotating very fast. So if you were to image this star plus this system as a function of wavelengths, in the visible continuum, you just see the star, just point source. But in the H alpha, we will see different parts of the disk as a function of wavelengths. So if we were able to measure the center of the image as a function of wavelengths, we see this signal, which is called a spectroasymmetric signal. And that was measured previously with a long-series spectrometer, and the amplitude was about 1 millisecond. And our goal was to recover this using the photonic lantern. But as I said, we knew that this is going to be challenging because our on-sky ground-based condition is not close to stable condition. Even after two-stage AO correction, there's a lot of tip-tilt jitter and low wind effect that makes these spectral traces fluctuate. All these aberrations couple into the measurements. So in this condition, it's very difficult to isolate the spatial signals from these aberrations. We need a clever way to work with this data. So I came up with this idea of filtering out the tip-tilt jitter. So if you were, in the previous video, we saw that the dominant waveform error is tip-tilt jitter. And if we were able to, if we observe this simultaneously with a PSF camera, for example, for this observation, we had the visible light going into the lantern and the infrared light imaged directly on the PSF monitoring camera. Then we can first find the PSF peak position in the PSF data. We can do this for every frame and assign these coordinates to the corresponding lantern frames, and then sort these lantern frames based on these PSF peak coordinates. So from this, what I'm actually doing is I'm filtering out the tip-tilt jitter, and also, importantly, I'm actually leveraging the tip-tilt jitter. I'm using it like a scan of the PSF across the lantern's input. And by doing so, I'm recording all the diverse responses of the lantern for different PSF positions. So once we have these sorted frames, we can make a map of responses for each detector pixel, and each pixel corresponds to wavelengths and each port, the output ports of the lantern. So that's shown in the bottom. We can see that there are some structures which are intrinsic responses of the lantern. So I did this for every port and as a function of wavelengths, and this is what it looks like. You can see that if you look at it very closely at H alpha, it's going, the video is moving across wavelengths. At the H alpha, every port is like moving slightly upwards and downwards, like wiggling, like this timing. So the physical interpretation of this is that let's define reference response maps as the response maps of a point source. Then what we are measuring is these reference response maps convolved with the true intensity distribution. So if you write like this, the image reconstruction becomes a simple deconvolution problem between the measured and reference response maps. So that means we need reference response maps. And for beta CMI, our target, it was easy because in the visible continuum, it is just like a point source. So we were able to model the reference response maps from the continuum and then interpolate in the H alpha region. And so that's shown in the middle panel. So now we can just solve the deconvolution problem. So here's the result. I first just assume, just simplify the problem by assuming that the image is just a point source, and found that the central position as a function of wavelengths. And this is the result. We can see that the major signal is along this green line, which is the disk's major axis. We were able to recover this 1 millisecond shift as along the disk major axis. And very interestingly, we were able to see something new, which is the asymmetry of the disk. There is the signal perpendicular to this axis. And this was possible because our centroid estimation precision is very good. It's about 50 microarcseconds. And I believe this is the best spectroasymmetric precision ever achieved in the visible. And also I want to note that this measurement was very efficient. We used only about 10 minutes of data. And then now I tried the full image reconstruction without simplifying the image. Unfortunately, the disk is very compact, so we didn't see much finer structures. But still, this demonstrates that image reconstruction works. And I'm very excited about this new on-sky result led by Aidan Walk, a PhD student at UH. He was able to measure the spin axis of our tear. So we are measuring very small the stellar rotation with this lantern. And I also demonstrated that this works with other lanterns as well. I applied the same technique to a 3-port lantern in the infrared, and we're able to recover the signals. So this is very exciting because for fainter targets, or if you want to use higher spectral dispersion, we might want to use fewer mode count lanterns. So I'm going to spend like a minute on what I'm working on next. So the beta CMI was a very bright star, but we want to be able to observe fainter targets, which are more interesting. And that means longer exposures, and longer exposure means more wavefront averaging. So in this regime, simply just leveraging the tip-tilt jitter doesn't work that well. So we need to actively stabilize the tip-tilt jitter and dither the PSF. And we already have the hardware for this, and we are working on this upgrade. And also I'm working on the calibrated observation mode. So beta CMI was a simple case. We were able to measure the reference response maps from the target, but we would need a separate calibrated observation. But the changes include any quasi-static aberrations or drift will couple into the measurements. So I'm working on more advanced frame sorting algorithms. Essentially, so for this work, I just use the PSF P coordinate. But we can use much more information than that, the PSF morphology, and even just other AO telemetry. So I'm working on developing this now. And I'm running out of time, so I'm also working towards making this for higher contrast. Then in the higher contrast, we need to really optimize the modes or the measurement modes. And I had a poster on this. In order to optimize the modes, we can use a photonic integrated circuit backend of the photonic lantern, and we can even tune the measurement basis to enable simultaneous high contrast and wavefront sensing. We have a photonic integrated circuit in the lab, and so please stay tuned about this development. And I will have the summary slide and take any questions. Thank you.
Okay, we have time for 1 or 2 questions.
Hi, thank you, Yoo Jung. Ben Sappy, UCSD. I was surprised that you were able to still use the 3-port lantern, so you're still sensing enough modes. Is there a limit to this? Like, could you potentially have a multi-mode fiber tapered down to a single-mode fiber and still be able to see the intensity changing, for instance?
Sorry, you mean, what's the question about using 3-port lanterns?
Yeah, so if you were still able to do it with a 3-port lantern, how many ports do you need?
Yeah, that's a good question. For spectral astrometry, which we are just measuring XY position, Three-port lantern might be enough for general. If you want to do more, resolve more structures, or if you want to go to visible, the three-port lantern might not capture, will have not much coupling, so there is consideration on that.
I think we're out of time, so let's save it for a coffee break. Let's thank Yoo Jung again.